Assalamualaikum to Dr. Izian as our lecturer for subject ECV 211 Advanced Structural Analysis. Today, our presentation is all about finite element analysis. As you can see from the picture here, they are all the product of FEA, which is the finite element analysis. Next, for the introduction, the background theory, the finite element analysis, FEA, is a numerical approach for engineering and mathematical physics issues. And the finite element method, which is the FEM, also known as the finite element analysis, FEA, is a computational methodology that is used in engineering to generate approximate solutions to boundary value issues. Simply put, a boundary value is a mathematic problem in which one or more dependent variables must satisfy a differential equation everywhere inside a defined domain of independent variables while also satisfying certain boundary conditions. Next, simply expressed, this approach is extremely beneficial for tackling problems involving complex geometries, loading, and the material characteristic for which analytical solutions are unavailable. The finite element approach includes simulating a structure with a tiny link elements known as the finite element, as you can see from the figure above. Each finite element will be assigned a displacement function, and this every interconnected element, including nodes and boundary line, is linked to every other element, either directly or indirectly through familiar interfaces. Next, okay, for the literature review, for 2.1, which is we're going to study about the conversion of the finite element. And the journal that we found out, which is a first course in the finite element method by David V. Hutton, which is the theory that they use a very basic issue with a known solution to show a conversion. As you can see from the figure, it show that the tapered solid cylinder with one end fixed and the other end subjected to the tensile forces as the figure A. Assuming that the displacement at the point of load application is of the interest, a first approximation is produced by assuming that the cylinder is uniform and has a cross-sectional area equal to the cylinder's average area. Because of the uniform bar is a finite element link or bar, their initial approximation is a finite element model. It comes into one element. The strength of the material theory is used to obtain the solution. Next, the tapered cylinder is then modeled as two uniform bars in series, as you can see from the figure C. Each element in the two-element model has a cross-sectional area equal to the average area of the corresponding half length of the cylinder and a length equal to the half the total length of the cylinder. As shown in the figure D, it can be seen that the mesh refinement is continued using a four-element model and so on. This is how David V. Hutton uses a very basic issue, which is known as solution to show the convergence. Next, I will pass to IQBAL.
Okay, thank you, Nazri. So I will continue for another part of literature review, which is subtopic of general procedure for finite element analysis. So the journal that been used, if you title of the finite element analysis program MSc Mark. So actually from this journal, we can say that for the first part, it explains about all of the procedure used for finite element analysis, and it's been specified for tapered bar. Okay, so for the first procedure is the problem statement objective. Okay, the tapered bar subjected to Agile load will be analyzed to predict the distribution of stress and displacement in the bar. All of the parameters that we use also being given stated from the figure. Okay, so for the next step is the analysis assumptions. So because the bar is thin in the width direction, so a state of plane stress can be assumed. And next is the mathematical analyzation. So basically, based on the assumptions that we stated, two different models will be developed and compared. The first model is 1D elasticity analysis, and also for the next model is the bar is discretized using linear two-noded 1D bar / truss finite elements having a uniform thickness within each element. So for the model can be also seen for the figure 3.2. Okay, so next step is the finite element model. Finite element model being created using software, and the step is the modelation using the formula. So from the formula that be used to calculate and get results in the post-processing step, which is some of the result is the distribution of displacement, the distribution of axial stress along x-axis, and also conversion of displacement and stress, and also some validity of the solutions. Okay, so for the next literature view, the subtopic of comparison of finite element and exact solution. So you are using the Journal of Structure Analysis of Non-Prismatic Beams. Okay, so for the from the journal, it's also state about the comparison, mostly about the software that we use. Okay, so based on the author, okay, so for the non-prismatic beam model, stated under tapered symmetric cantilever about the solution using the finite element software, which is Abacus. Okay, for the figure, which focusing the effects induced by constraint in left hand side and load distribution in right hand side. The distributing coupling constraint has been made using point 00 and 0L as reference points. So for the post-processing stage, SEP 2000 software has been used to estimate shear stress only in points, which is the cross-section, center and boundaries. So the summary of the result can show that the data provided by SEP 2000 for structural stiffness with errors larger than 2% and also maximum magnitude of shear stress that up to 30%. Pass to another presenter.
Okay, thank you, Iqbal. Next, I will proceed to the methodology, which is 3.1 manual calculation flow. So first, we idealization the problem. Then we divide the element. Then we label the element, which is the one first element, second element, and third element. Then after that, we label the node of the element, which is node 1, node 2, and node 3, and node 4. Then after that, we calculate the area based on the formula given. So for the cross section shape, which is the circle, so we use the formula for the circle shape, which is pi r square. Then we calculate the K1, K2, and K3 from the formula, which is A E over L, and the metric 4 by 4, 2 by 2, sorry, 2 by 2. Next, after we calculate the K1, K2, and K3, next, Nazri, combine the K, or the K1, K2, and K3. We substitute into the one metric. Then after that, we substitute into the formula. After that, we substitute the value into the formula, which is force equal to E, displacement, and K. Then after we substitute, we solve it, and we get the displacement 2, displacement 3, and displacement 4 element. Then after that, we calculate the another forces, which is reaction 1. So we get the negative 200 Newton. After that, we can obtain from the displacement, we can obtain the strain, which is the formula of strain is B times metric B times matrix displacement. So we get the strain. After we get the strain, we can calculate the stress, which is the formula is the stress equal to E times strain. So as you can see, the stress for element 1 is 1.7, stress for element 2 is 2.53, and stress for element 3 is 0. So next is we calculate the axial displacement. So this is the calculation to find the range of 0, the x from 0 to 60, which is we calculate the formula based on the range. So as you can see, the second range is 60 to 100. So for the displacement 2, so we solve it, integrate as usually to get the displacement 2. So next, okay, this is the displacement. We write it back and for the range 0 to 60 and 60 to 100. Next, we calculate the stress based on the axial displacement that we get. We need to substitute the axial displacement into the formula, which is differentiate the axial displacement to get the stress. So as you can see, we get the stress for the element 1, element 2, and element 3. So for the stress distribution, after we differentiate the axial displacement, we get the stress distribution, which is you can see at the green at the green picture, 0 to 60 and 60 to 100. As we calculate our AO, which is 78.54, and our E is 6.6 times 10 to power of 6, and our force that we obtain from the problem given is 200 nodal displacement. So we need to substitute the value given, which is AO, E, and F, to get the nodal displacement for element 1, element 2, and element 3. Also element 4 for the next slide. Okay, after we get the axial displacement, so we can obtain the axial stress. So we also substitute the forces and AO. Actually, I need to correct the axial displacement, which is it is based on the not the element. So we obtain the axial displacement for node 1, node 2, node 3, and node 4. So from this axial displacement from the node, we can obtain the stress for the element. So element 1, we can get 1.7 Newton per centimeter square, and the stress for the element 2 is 2.55, and the stress for the element 3 is 0. As you can see, as your stress. So after that, these are the final result that we obtain from the manual calculation, that we need to compare it with the software calculation. That's all from me. I will pass to Afif. Thank you.
So I will present about the software analysis by the set 2000. So for the first one, first step is the idealization of the element. So we split the element into three, which is element 1 until 3. Each element have the different cross section. So we go to the next step is modeling technique. We create a grid line, and then based on the grid line, we can assign the property, like the change the material property, like we use the aluminium. So we will use the modulus elasticity for the aluminium. So next is we assign the frame release for the moment and torsion for the each element. And then we define the frame property, as we have the three different of the cross section for the three different of element. And then we assign the two load to 200 Newton load at the end of the element 2. And then we run the analysis and we get the nodal displacement. Next, this is the illustration for the idealization. We have three different elements. So we class it into three elements, which is element 1, element 2, and element 3. So from that, we analyze this element by using set 2000. So this is the grid line that we create from the one element to one element. So the first element is the length is 0.3, and the second element is 0.3 meter, and the last element is element 3. The length is 0.4 meter. Next, so this is the material property that we assign. So actually in this project we use the aluminium as our element. So we assign the modulus of elasticity is 6.9 for the value of E. And then we release the moment for the each element, which is for the torsion and for the moment for the each of element. So next we define the property for the frame. So for the first element, we have about 0.0117 meter square for the cross section, and for the element 2 and element 3, we have the cross section, which is 0.85 exponent for negative 3. Negative 3 the cross section. So each element have the different cross section. So that's why we need to assign different cross section. So and the last one, we assign the load, which is 200 Newton load for at the element 2, at the end of the element 2. Then I will pass to the Nur Aniza.
Okay, thank you, Muhammad Hafiz. So I will continue with the analytical result, numerical result, and software result for manual calculation and comparison between the manual calculation and software output for the result and the discussion. So as we can see here, for nodal displacement, for numerical and software we got the same value, which is at for the element 2, 3 and 4 we got the same value, but for analytical nodal displacement it might slightly different. For the nodal element 2 it might be less than for the numerical and software output, but for the nodal element 3 and 4 it was bigger than the nodal displacement for numerical and software output. So for the Azure Stress project, we got same value, these three things for the analytical, numerical and software Azure Stresses. And next, okay, so for the validation of software result with numerical result for finite element method, as we can see here, for the manual calculation and for the software output, based on how my friends talked just now about how to calculate by manual and by software, we got same value. So that for the nodal displacement, we have no difference, and it also same to the exact stresses, which is with the manual calculation and the software output also same value, and the differences was be zero lah, because it was no difference between both. Okay, next. So for the comparison between exact solution and software analysis, what can say here? For nodal displacement exact, the differences between the software output was 14% for the element 2, and element 3 was 24%. For element 4 is 31%, which is the range of the percentage is between 0 to 31%. So the difference of nodal displacement actually is happen when the bar is cut into more parts, and the nodal displacement will become closer to the exact value. So for the Azure stress of the frame element, the comparison between the exact solution and software analysis, no differences value, which is because the value is same for both, and this is acceptable because the exact solution and the software have 0%, which indicates the result to obtain is satisfactory. So the validation of software and can be validated if finite element method by manual calculation and software was have a slightly different small difference percentage. So it can be said that finite element method is valid for this model, and I think for the differences that we have for the nodal displacement are due to the modeling, and some errors are due to the numerical solution, and it is known as a error of idealization and discretization, reliable for predict types of errors. So that is for the result and discussion. Next, I will pass for the to Nazurah.
Okay, in the conclusion, the manual calculation and software analysis, which is the SAP 2000, can be used to solve the finite element problem. As you Niza present before this, we can see the percentage differences. Percentage is zero, which is we can reliable on this method, finite element problem method. Then we could analyze that the comparison between the manual calculation and software values are both sufficient, accurate to predict the values of nodal displacement and axial stress of the model. What makes there is the slight different occur is maybe caused by the minor mistake in the manual calculation, since we have to deal with the numbers. For example, the decimal point. The advantages of the using SAP 2000 is that we can obtain faster result rather than the manual calculation, because the manual calculation need the focus, more focus, rather than we use the SAP 2000, which is the computer work on it rather than we work on it. Then the last conclusion that we learn from this project, which is the manual calculation and the software analysis SAP 2000 can be used to solve the finite element problem. That's all from us. Thank you.